So it's again my pleasure to invite Christian Ikenmeyer, who has been one of the sort of persons who's really pushed the boundaries of GCT. So he'll be talking to us about highest weight vectors, power sums, and Young tableaux. And this is his first talk. He'll give his second talk, I think, on Tuesday. Yeah.
Yes. Thank you so much for the introduction.
Yeah.
Yes. So this is going to be this is the workshop, right? So I will try to actually. So I designed this talk to be more of kind of a workshop talk, while the other one is a usual conference talk. So this is going to be, so I'm focusing on some special aspects of this paper here, this implementing GCT on the separation of orbit closures via symmetries. This is with Umangatan Kandasamy. And so yeah, I'm going to show you what the aspects are that I'm going to focus on. And so the second talk is the usual conference talk where I just present the result and present the whole proof overview and everything. But I think this result here that I'm going to present is interesting on its own. So it's about the power sum, like as you would guess. It's about the power sum polynomial. So your group is the general linear group. So I'm working over the complex numbers here all the time. And the polynomial P is the power sum polynomial of degree D. Right, and now it is the case that, and I'll explain this now on Tuesday, that we do have formulas for the multiplicities of the coordinate ring of the orbit. So I'm not talking now, I'm not going to explain now what that actually is, but there's this notion that where we do have formulas for that, and we want formulas for these, for the multiplicities on the coordinate ring of the orbit closure. And I'm not going to define this here at the moment, but this paper gives a connection between these two notions here using a tableau theoretic interpretation of both of these multiplicities. These are natural numbers, and there's this connection. And now a connection between these two, where we understand the one thing here, we do have formulas, and we want formulas for that, and we now establish this connection. Now this leads to the first multiplicity obstructions for orbit closure containment. That is based, and this is based actually only on the symmetry groups of two polynomials. And so this will be the second talk. And in this talk, what I want to do is I want to give a tableau theoretic interpretation of this multiplicity. So I want to introduce what are these things, what is this, what is happening here, so how is this defined, and what is actually how could you now go and just compute this, right? So at the end, you should be able to compute this multiplicity for whatever parameters you want. You can at the end go and implement it and just compute it. Okay, so then in the second talk, we will be all set to actually understand like this other multiplicity and the connection between the two that actually makes the whole thing work. All right, so I didn't define anything yet, but I just want to define this now and tell you about the tableau theoretic interpretation. But any questions so far? I mean, obviously there are some questions, but I mean, I postponed some of the things and hope that that's all right. So let me define, okay? Okay, so, this is basically about the definition, so representation of theoretic multiplicities and highest weight polynomials. Then the main theorem is actually this explicit construction of highest weight polynomials for the power sum via Young tableaux. So this gives a definition of this multiplicity just using Young tableaux. You can implement on your own. And I want to give a proof sketch of how this is done. All right. Oh, now this is going to be problematic here because, but I can move this. Okay, why not? I can move this down here. Does it help? I'm not sure. Got to be constantly moving these boxes around now. It's going to be interesting. Can I do anything against that? I probably not. This is just my life now. Okay, so I want to introduce some notation. So this is actually a slide that covers like the whole GCT setup on one slide. And on the left-hand side, there's the general setup. And on the right-hand side, there's an example. And it would be nice to, I thought it would be nice to have all these things on one slide for once. So SIMD CM should be the homogeneous degree D component of this polynomial ring, x1 up to xm, are the variables. Right, so for example, and these are the easiest examples, and unfortunately in the easiest examples, all parameters are equal to 2. So these are homogeneous degree 2 polynomials in 2 variables. So x1 squared, x1, x2, and x2 squared form a basis of this 3-dimensional vector space here. Right, it's just a bit of a funny way of writing this vector space. And our group G should always be GLM in this whole talk, okay? And it acts linearly on this vector space this is what is called the canonical pullback. And sometimes people put a G inverse here, sometimes people put a G transpose here, and sometimes people make it a right action to put an XG of a row vector, things like that. Doesn't really matter. All these things are basically the same, but of course, when it comes to the details, when you do calculations, then it actually matters. So what I chose here in the example is a matrix that is self-inverse and self-transpose, so we cannot mess anything up here. Oh, but I of course did mess up this. The parentheses should actually go here. So, but I have a drawing tool here. Look at that. All right, so that's better. Okay, so this one flips x1 and x2, right? So if you apply it to x1 squared plus x1 x2, you'll get x2 squared plus x1 and x2. Do I have this? Okay. Okay, now okay, let's have a sub. Oh, now, oh, no, I don't want to. Okay, let's hope that this will work. So let's have a subvariety here of our space of polynomials, like a closed subvariety that's also closed under the group action. And the standard example is, let's look at the set of all polynomials that are homogeneous polynomials squared, right? So there exists some coefficients alpha and beta such that the linear form is equal to alpha x1 plus beta x2, right? And this is our x. But our x, actually in GCT, we're oftentimes interested in the case where this is an orbit closure, right? Where you take your group and you apply it to your polynomial P in all kinds of ways, and then in the end you take the Zariski closure of that. And here in this case, it would be the GL2 acting, and your point is just x1 squared, and you're moving x1 squared around. This will exactly give you this set here. You get all the linear forms squared. And now we want to study the functions that the homogeneous degree delta polynomials in the coefficients of these original polynomials, right? So kind of meta polynomials. And this is just this polynomial ring over our base vector space, homogeneous in degree delta, and we give this name, right? It's the sim delta sim DCM. And here, and we saw actually an example in my first talk. I'm not sure if people remember, but maybe let me therefore explain this again. So sim2 C2 is a 6-dimensional vector space spanned by a squared, ab, ac, b squared, bc, and c squared, like all these different combinations of a, b, and c. And those are the coefficient functions of your original polynomial. Like, for example, the most well-known polynomial here in this space, the most well-known vector is b squared minus 4ac, the discriminant, right? So that one is here in this vector space. Okay, so we want to study that. And in fact, yes, so the group acts linearly on this vector space, also by a canonical pullback. And again, there's this issue with the -1, with the inverse or transpose. And so this makes this a G representation. So here, if we, for example, act on a squared plus ac plus b squared, and we are switching this is saying switch the roles of x1 and x2 here on that polynomial. What it does is, well, a is the coefficient of x1 squared. Well, now it should be, I mean, so if you apply this here, it's the coefficient of x2 squared, right? So this maps a squared to c squared. AC is mapped to CA, which is the same as AC, and B squared is also just mapped to B squared. Right, so this is the type of action that we have here. But of course, you can take all different types of matrices that you want. It doesn't have to be this specific one here. Now, I of x should be the vanishing ideal of your set X. These are the polynomials that vanish on the whole set. So wherever you evaluate them on the set, you always get 0. Right? This is called the vanishing ideal. And yeah, most notably, b squared minus 4ac is in the vanishing ideal of the set here. Well, you have to do some little calculation and you will see that. And you can also look at the homogeneous degree delta component of this vanishing ideal. You just restrict yourself to the homogeneous degree delta polynomials, right, that vanish. No problem. So here in this case, it's actually the case that your homogeneous degree 2 component is exactly spanned by the discriminant. So it's a one-dimensional vector space. So it's a linear span of just the discriminant polynomial. That is what is in this vector space here. And now your X is closed under the action of the group. This also makes your vanishing ideal homogeneous component also closed under this group action, and therefore, yeah, it's a G representation. This means that it's a G representation, right? So, for example, if you act on the, yeah, not sure if that's actually an example of this, but you have the discriminant and you act on the discriminant with some group element, then what happens is that one has to calculate this, that you just rescale the discriminant by the determinant squared. All right, so in particular, this vector space here, this vector space is indeed closed under the group operation. This always happens. And you can define the coordinate ring now. And the coordinate ring is you take all functions and you divide out by the vanishing ideal. So this is a quotient vector space, right? It's just a quotient space. And here in this case, for example, this vector space here would have a dimension of, well, it's 6 minus 1, because the original vector space had a dimension of 6. Here, this is the 6 here. Minus 1 is 5. Minus 1 because the vanishing ideal in this degree had a degree 5. Alternatively, sorry, had a degree 1, minus 1. So alternatively, you can also define it, and this is nice, and we will use that. The coordinate ring is, this is a more of a hands-on approach. You take all the functions and you restrict that domain of definition just to X. And then you just look at what are the functions, I mean, what are those functions? Right, and that gives you an isomorphic ring. And yeah, now I can move things up here. It's going to be a hassle, but anyway. Okay, so now this is going to be degree delta functions. And yeah, as we did here in this example already, right? In degree delta, you can do this by just saying, I take the degree delta functions and mod out the degree delta part of the ideal. So this is a finite dimensional vector space. That's a finite dimensional vector space. You take the quotient, get a finite dimensional vector space. Right here, this is what we did here with the 6 minus 1 equals 5 here. And yeah, so this is a finite dimensional vector space that has a group action, and this is a sub-representation of it. So if you take the quotient, you still have a representation. This means that indeed this coordinate ring is actually a G representation. So that's the whole setup, right? So this is usually what we look at in general, right? And then this is one example, and we are particularly interested here in the power sum polynomial P and see what happens for the power sum polynomial. Okay, so that was the standard setup. But we are interested in a tableau theoretic interpretation. So I have to talk a tiny bit about these tableaus as well. Right? Okay, so a partition is, I mean, it's not that well, I guess the first talk is just a while ago, right? So I just, let me just therefore say these things again, okay? So a partition is a finite non-increasing list of natural numbers. Here's, for example, 5331 is a partition. And you can, for every partition, you can associate its Young diagram, right? It's a top left justified array of boxes, and in the ith row, you have lambda I many boxes. So here's 5331. Right, and you can transpose a Young diagram, and you just write lambda transpose. So it's 5331 here. And you can look at the partition that happens for, that is the transpose, right? So in the transpose would be the partition 43311. Okay, so that is the transpose partition. Indeed, we actually often identify a partition just with its Young diagram. Those are the same types of objects for us, oftentimes. And there's a notation for partitions and Young diagrams. This is this notation here. It's a lambda is a partition of D. So the Young diagram has D boxes, and it has at most m rows. So this is little m here. And if lambda has D boxes, then there is an irreducible SD representation of type lambda, and we will write it like this, also called the Specht module. And if lambda has at most m rows, then this one here, we can write this one here as an irreducible GLM representation of type lambda. And it's called sometimes the Schur module or the Weil module. So we do know explicit constructions of these. So we basically know, we know a lot about these, in particular explicit bases, using tableaux actually. So these are done, these are defined using tableaux, and I will talk about this in a second. So in the Young, what is a Young tableau? A Young tableau is now, or just a tableau, is a map from the boxes of the Young diagram to the natural numbers. So you're writing natural numbers in the boxes. It's an assignment of numbers to the boxes, like this one here. Just assign some numbers to the boxes. And it's called semi-standard if each column is increasing from the top to bottom, and every row is non-decreasing from left to right. Okay, so this one here is certainly increasing top to bottom here in each column, and it's also non-decreasing, right? So it's like a weakly increasing from left to right. That's called semi-standard. And we have two more interesting tableaux. The left one more interesting here in this talk than the right one. The left one is the super standard tableau. It's like you have in row I, entries I. That's like the simplest type of semi-standard tableau that you can think of. And we write it as this specific S index lambda. And the column standard is where you go through the columns and you just say 1, 2, 3, 4, 5, 6, 7, and so on, right? But you go column wise from left to right, top to bottom. That's the column standard tableau. And these types of notions are useful now to express the coordinate ring of this orbit closure. So we'll see, we'll see that. Okay, let me talk about these multiplicities, because we want to understand the multiplicities, right, of a coordinate ring. Now, what is that actually? So when you have a representation V, and this is the example, it's like sim delta, sim d, cm, like this one here. You always think in the back of your head, you have this 6-dimensional vector space with this a squared, ab, ac, b squared, bc, c squared, right? You always have this in your back of your head. Now, every representation like this is always like a finite dimensional vector space, decomposes, but not in a necessarily unique way, into a direct sum of irreducible representations. So this always happens. You always have a direct sum, and the sum is overall partitions lambda that have at most m rows. And some of these will be isomorphic, and we group together isomorphic copies. Indeed, actually, we group together isomorphic copies and we count them. And the C lambda is actually how many of this type lambda will occur there. Well, it sounds a bit abstract. We will see in a second how this can be expressed in a different way. Well, you have in this example, you have the same thing. You just have a different name for this coefficient. Just call it A instead. And these are non-negative integers because you are just counting how many copies there are in your decomposition. And they are independent actually of the decomposition itself. So the decomposition might not be unique, but these numbers here, they are well-defined, independent of the decomposition, and they are called the representation theoretic multiplicities. So that would be a multiplicity. And this specific coefficient here is called the plathism coefficient. And now there's a way of actually defining this very hands-on, and it's in this fashion here. This will allow you actually, whenever you have any representation, to find out what are the multiplicities. This is one way of doing it. Every irreducible GLM representation contains exactly, up to scale, one so-called highest weight vector. And what's the highest weight vector? a highest weight vector is you have a, so it's a vector F where if you apply a diagonal matrix to the highest weight vector, you have action of GLM, right? So this is a diagonal matrix in GLM, you apply it, then your vector rescales by alpha 1 to the lambda 1, alpha 2 to the lambda 2, ... alpha m to the lambda m. This product here rescales your vector. Well, this says that your vector is of weight lambda. And then additionally, the second property is that when you have an upper triangular matrix with ones on the main diagonal and you let that act on your vector, you get exactly that vector back, right? So it's fixed under this action. Yes. So this means that, in particular, I mean, these properties tell you what, if you now start with a 6-dimensional vector space, then these two properties tell you that you can find now the highest weight vectors, right? This is now a problem in linear algebra, right? So as a grad student, I did this with MATLAB, for example. This is probably the worst way of doing it, but you can, it's the definitions give you basically exactly what you should be doing, and you just find these vectors. Now, those vectors are extremely nice because true irreducible representations are isomorphic if their weights, the weights of their highest weight vectors coincide. And for example, one of the highest weight vectors is the discriminant b squared minus 4ac. And so, as I said, if you act on the discriminant, then the discriminant is rescaled by the determinant squared. And this means that the discriminant is in fact a highest weight vector of weight 2, 2. Why is that? Because if you act now with a diagonal matrix, so it's now that matrix looks a bit simple actually. Not entirely sure if I do have access to yep, I do have access here, okay. So I'm sorry for like my font here because this is my mouse. Okay, so if you have that and you apply this to F, the determinant squared is alpha 1 squared times alpha 2 squared. Oh my goodness, my handwriting with a mouse is a bit ridiculous. I should not do that. Okay, so this is how it scales. So certainly the vector is, a vector with these properties is a weight vector of weight 2, 2, and it's also a highest weight vector because the determinant of this matrix here is 1, right? So this means that it's not gonna, it's gonna be fixed under this operation. And now the multiplicity is instead of using this complicated way of defining a multiplicity, now this is extremely hands-on. The multiplicity is the dimension of the highest weight vector space. Right, so yeah, any representation you have, you just want to know what's the multiplicity of lambda, you just take the you just compute the highest weight vectors of weight lambda and that's it. The dimension is precisely the multiplicity. So you only have to care about the dimension of the highest weight vector space and nothing else. So for example, for a coordinate ring, and this is what we want to do, coordinate ring of some homogeneous degree delta component on some variety x, what you would need to do is, well, you look at the highest weight vectors that exist on the whole space, you restrict the domain of definition to x, and you take the dimension. And that's, so you don't, this is a linear algebra question, right? This is there's no, using these two definitions, this is a problem in linear algebra. You just need to understand what are these highest weight vectors of weight lambda here in this set. And at that point, when you know those, you can just restrict them. You can evaluate them, say, at a lot of points in X and see what is actually the dimension of that space. Say, maybe if you do this symbolically, it's actually a proof even. Okay, so this is extremely hands-on here. So yeah, so you could implement this now. This should not be an issue if you wanted to implement that. Yeah, Demi gives you some papers where this type of approach has been, oh, this is not so bad, I can put it here. Some papers where I use that type of approach, just a list of papers where this is used for different parameters setups here. Yeah, so this is a powerful technique that can be used for computing, for answering actually all kinds of questions that have been open. Even in geometry, these things have, yeah, these things have been, some questions have been open and one can actually answer them using computer support, but also get theoretical results about the evaluation of these vectors. So it's LP hard. There are some efficient algorithms for low tree width, for example, and things like that. But those are just papers of me, but there's many other authors that actually use the similar, very similar approaches, because this is extremely classical. So this is not anything like I invented this, but this is like completely classical using these tableau techniques. Okay, so we want to study, as I said, we want to study now in this specific talk, the power sum, and yeah, so this is our group, and we want to understand this vector space in terms of tableaus. And so to state the result, let me try to say something about about tableaus and their connection to tensors. Okay, so TRC, if you have a tableau, then you want to maybe get some entry of the tableau, that should be TRC. And if you have you get some standard basis here of your vector space, and you want to transpose your tableau lambda. Okay, now there's a one-to-one correspondence between a tableau. So somebody gives you a tableau with entries 1 up to m, and you can create a vector out of this. This is a tensor in the tensor power, and this is the number of boxes that lambda has. Right, for each box you get a tensor factor here, and you just tensor them up. That's it. You just tensor up the basis vectors that are in your tableau. So if your tableau just has a 1 and another 1, this is just E1 tensor E1, right? And if your tableau has some other entries, you get some other tensors. Okay, so this is literally, this is the correspondence, right? So that's for each tableau you get a basis vector, but also vice versa. But now, why is this interesting? Because you have a natural action of your general linear group on the tensor space. Right? So this gives actually a vector space isomorphism between your tensor space and linear combinations of tableaus. So you take a vector space, it's a vector space of linear combinations, formal linear combinations of tableaus. And so this will give actually an action. So you have your usual action on the space of tensors from your general linear group, but now you can actually let it act on a tableau. So this, for example, this matrix here would send E1 to E1 plus E2. Okay, so now you want to let it act on a tableau like this. So this means that that a 1 is replaced by a 1 plus 2, and this is expanded multilinearly, like on your tensors. Right, so every 1 is replaced by a 2, but it's actually it's exchanged by a 1 plus 2, right? So this is gonna be 1 1 1 2 2 1 and 2 2, right? So these 4 tableaus is what you get when you let it act like this. So now you have an action actually on this vector space. Very nice. And you want to define now the vector space of shuffle relations. This is a linear subspace of this vector space, and this is what makes this is basically what is the correct space in which you want to work with the tableaus from a representation theoretic standpoint. So these are the shuffle relations. There are some other shuffle relations that also work. I just take these ones now. There are several papers actually explaining what types of shuffle relations you can actually take. So that's a vector space K of lambda, and it should be spanned by T plus T prime, where T prime is the tableau that arises from T by switching 2 numbers within 1 column. And a more complicated one that I'm not going to read right now. It's not so crucial now because I want to first give an example here of why this is interesting. So what you take is you take your space of linear combinations of tableaus, and you quotient out this vector space, right? And what you get, so this is the theorem, is that you get the irreducible representation of the general linear group. And so let me maybe give you an example here. So the 2 1 is the same as minus 1 2 in this quotient space, because because of this here, because it says that so if T plus T prime is 0, right? Because this is what it means when you quotient out this. This means that T is equal to minus T prime when where T prime arises from T by switching 2 numbers within 1 column, right? So these are negative of each other. And yeah, so let me maybe also say what's the second one here. So the second one is T minus the sum over tableaux S. This is the complicated one that actually makes the representation theory really a bit complicated. But you sum over all the S where you have two fixed columns and a fixed number of entries, K, and the sum is over all the tableaux S that arise from T by an operation that is exchanging the top K entries in column J with any K entries in column J prime, preserving the internal vertical order. So there are different ways of phrasing this, but they are all rather complicated. So let me maybe give an example of this. This means that if you have a tableau like this, then now you can exchange the 1 and you can exchange it with a 4 and you exchange it with a 2 and and you sum over all the possibilities. Right, you would have these things and now you can say maybe I don't like it like this because this is not semi-standard. Let me maybe also make this semi-standard. So I'm switching the sign here, getting this. So you do want to actually make it always semi-standard because the basis of this is, and this is a theorem, is given by exactly the semi-standard tableaux. Maybe one more here is so starting with this tableau is not semi-standard because the 1 is on the right-hand side of the 4. But now you can say, okay, I put the 1 and the 4, I switch the 1 and the 4, and I also switch the 1 and the 2. And now I see, well, this tableau here is certainly going to be 0 because, and let me try, because I do have a column here that has a repeated entry. And once you have that, then you see already by this example, so this tableau here is equal to its negative, so it must be 0, right? So this is going to be cancelled. Let me also say about the superstandard tableau. If you got a superstandard tableau and you have an upper triangular matrix, you already see that this is going to replace numbers by lower numbers if you do this operation. But if you get lower numbers, you will get repeated entries, right? So whatever you do here, whatever alpha, beta, and gamma is, this will be fixed. There's no way around it. This already tells you this is a property of the highest weight vector, right? The superstandard is a highest weight vector. Okay, so and this is the type of way that you want to calculate with the tableaux, and this is completely well defined now, and you could implement this, right? No problem. Now, if every number appears exactly once, then you get actually the Specht modules, those are the irreducibles of SM. Just saying. For stating the theorem, I need an operation that's called averaging. I just gave it that name. And so you're starting with a tableau, just has entries 1 up to delta. And I have a map that now maps the entries 1 up to delta to some other entries that come from 1 up to m. And I want to define what it means to apply this to a tableau, and that's completely naively. So I have a map, say that maps 1 to 2, 2 to 2, and 3 to 1, and I apply this to this tableau. What it does is, well, the 1s are mapped to 2, the 2s are mapped to 2, and the 3s are mapped to 1. Okay, and I'm always working now in this quotient space, so I already see that here there's a repeated 2, for example, and this is going to be the 0 vector. This one here was not the 0 vector, but this map here now maps this to the 0 vector here. Okay, so I'm always working in this quotient space. So this here is the quotient space that I was just talking about. And I want to say, okay, I mean, I know now how to apply my map phi. I want to apply all maps phi and sum over that. And I mean, you might call it an orbit average. I'm not so sure if that's the best name, but what you want to do is you want to do some large summation of all maps that are possible and apply them to your tableau. So for example, if you do the M32 to your tableau, then you're replacing, on all ways possible, in all ways possible, and there are 8 ways possible of replacing the 1s, 2s, and 3s by 1s and 2s. All right, so these are all the different ways. And yeah, here in this case, of course, you will see that there's always going to be some repeated entry in the first column because you only have 2 numbers and three boxes. So this is certainly going to be 0 because all of these will be 0 in your, all of these 8 here will be 0 in your quotient space. Okay, but so that's your capital M, and I can now state, so this is a theorem here now. So the theorem is that you can now understand this highest vector space, and this means that this gives you the multiplicity, right? So the highest vector space, its dimension is the multiplicity, right? So you want to just understand that space. So you're starting with a power sum, and you have your group, and you have a partition. And now this vector space here is generated by functions. And those are exactly these functions here. You take a group element and you map it to an inner product of the super standard tableau and this vector here, which is you take your tableau T. So T should be any semi-standard tableau of shape lambda. So you fix a semi-standard tableau of shape lambda. You have entries 1 up to delta, and every entry appears exactly capital D times. And you apply M delta M on it, right? It's like this. It's exactly like this. You take a tableau, you apply it, you get this large sum. And now you also apply this, this element G, right? So it's a function on the group. It's not actually a function on the orbit closure. It's a function on the group. I'll tell you in a second why that's all right. Mm-hmm. So this is a function that if you're given a group element, you get some, this is a complex number here, right? So this inner product, I just define it. So you got two semi-standard tableaus. It should be like delta ST, like the canonical delta. Just literally you want to expand this and then just check the coefficient of your super standard tableau. That's it. That's the function. Right? This is just you do this, you take the coefficient of the super standard tableau, output that. It's a function. It's a function on the group. So now one has to understand that why is this well defined? I mean, I want this to be a function on the orbit closure. So just recall these things. For well definedness, I have to not do very much. First of all, I don't actually have to define this on the whole orbit closure, because it's perfectly fine to define a function just on the orbit and just say that it continues to the closure by continuity, and that is perfectly legitimate. So if it's well defined on the boundary, but here in this case it will be well defined on the boundary. And then the well definedness, one more thing is that if you have a point now, so you want to define what is the value of your function on some point in the orbit. But the thing is, if you have a point in the orbit here, then it's not unique. So it might not be unique. What's your group element that gets you to this point? And so Q is in GP. So Q must be equal to GP, but G is not uniquely defined. It's only unique up to a right multiplication with a stabilizer. So you have a stabilizer of your point, of your power sum, and that is a wreath product of a bunch of, you got a bunch of cyclic groups and a symmetric group. So the wreath. So you see already the stabilizer of this. What could that be? I mean, there's a symmetric group commuting the summons, and each one here has a you can multiply x1 by a dth root of unity, and that's not going to change the polynomial. You can do the same for all of the different variables. You can multiply the variable with a dth root of unity, and it's gonna not change the polynomial. So that's what I mean by this stabilizer here, and so now you would have to show that when you have a different point, a different group element, you get the same value here in this expression. And then this means that you have a well-defined function now on the orbit. And that is the case indeed. So you can do the check for the cyclic part and for the symmetric part independently. Well, this is maybe like a tiny example here. For the cyclic part, for example, say capital D is 3. Delta being 4 and M is 2. And you take some third root of unity here and you apply that part of the stabilizer. So this is part of the stabilizer. And if you apply this to this tableau here, what is going to happen? It's going to happen that that this is going to be rescaled by omega to the 6, because there's 6 ones, and each one is going to be rescaled by omega. So this is going to be rescaled by omega to the 6, which says that this is the same vector. Okay, so and well, this is an example, but it holds in general that that the cyclic part is not going to do anything to any of your summons, and the symmetric part is a slightly more subtle. You actually need that your M is an operation that maps to, that is kind of a symmetric type of operation, right? So these two sums are actually the same sum, but H will actually permute the summons, which is, of course, yeah, it's the same vector, right? So this indeed gives you a function, at least, I mean, we were verified, it gives you a function on the orbit. We're not going to verify now that it actually also gives you a function on the boundary, but it's also not so difficult because you're only doing polynomial things here. There's no, yeah. Anyway, okay. So this gives a function now here on our orbit closure, and yeah, I want to give some examples here of how to, apply this, right? Before, I mean, I want to, of course, say something about the proof, but that's not the main interesting thing now. Maybe I want to say something about how to apply this, because this is extremely hands-on, right? So, for example, you can take this tableau here, and I just call it here the discriminant. We don't know it's the discriminant at this point, but this is going to be the discriminant. And we can evaluate it, say, at this power sum, right? Because this tells us how to evaluate something at a specific power sum, but also in the orbit closure of the power sum. But yeah, in particular, if G is the identity, we can just have a look, right? So what happens if I evaluate at the power sum? Well, I evaluate M21T. So this is my tableau T. And I'm now mapping all the ones and all the twos to 1, right? But this tableau is certainly going to be 0. So this means that this function, whatever that function here is going to be 0 on the x1 squared. And I can also do this for, yeah, it actually follows that the function vanishes on the whole going rank 1, because yeah, you can take any G. The G, an action of G is not going to change 0 to anything else, right? So therefore, this all vanishes on Warring rank 1. And so you note you didn't actually have to do any like interesting calculation. Like there's no b squared minus 4ac where you had to like do some calculation. This is completely immediate here now, right? It's just playing around with these tableaus. And also you will see that indeed for Warring rank 2, this function is non-zero, because you do want to know that the function is non-zero, right? It's not always clear that the function that you define in this fashion is non-zero, but you can do it because you just plug in M22 of your tableau. You do the summation here. And yeah, so this summation has 4 summons now. And yeah, so 2 of them are actually going to be 0. So can I, yeah.
Okay.
So this one's going to be 0. This one's going to be 0. And these 2 are actually the same, because if you're switching these 2 entries, you get a sign change, and you're switching these 2 entries, get a sign change. So you're actually getting this tableau here twice. This is 2 times this tableau here. And well, that's non-zero, but you want to have the function to be non-zero. Indeed, now you contract with the yeah. So you contract with the superstandard tableau. Did I? You have this. Okay, so there's the 1/4. I mean, it's not so important to have this number here completely correct, but you do see, I mean, this certainly is, this is the superstandard tableau, right? So in particular, the inner product is non-zero. The 1/4 is just to get the exact same correct number for the discriminant in the end. That's not so important, but you do see this is a superstandard tableau. There's more complicated things, like for example, there's an invariant by Aronhold, there's a classical Aronhold invariant that really is this tableau here. And this tableau here vanishes on Warring rank 3, and you immediately see, actually one can immediately see this, right? Even though you don't see immediately that this is the 0 function, you see Warring rank 3 has no chance here that this is going to evaluate to anything non-zero. Because what you need to do now is you would need to look at M4(3), right? 4(3) is gonna, you're replacing the numbers here by only 3 different numbers, right? But if you are replacing, like without loss of generality, you will replace 1 by 1, 2 by 2, 3 by 3, and then you are left with replacing 4 by either 1, 2, or 3. But you will always, for 1, 2, and also for 3, you will get a repeated entry here in one of the columns, right? So you immediately see it's the same kind of argument that you did here for the discriminant, that vanishes at Warring rank 1, you see that the Aronhold invariant vanishes on Warring rank 3. You just see this immediately here from this description. And yeah, you can calculate that it does not actually vanish on Warring rank 4. Actually, you can be completely explicit and give a point in the orbit closure where it does not vanish. So this is not so difficult to actually see this. You could now actually take this point, describe it explicitly in this orbit closure, and plug it in and compute it's non-zero. It's not difficult. It's actually, yeah, it gives you, the summands are, there's a very high amount of symmetry here that you can use to see that this is not actually zero. So this gives, yeah, this is already interesting, gives an interesting equation here. Right, okay, so that is great. So all these kind of things you can actually do with just having this type of description. And yeah, let me maybe say, if you have this type of description, what's the main benefit? I mean, it's of course nice that we can do this and we can run it on a computer, and that's all nice. But the main really nice thing here about this is that you can actually relate now the coordinate ring of the yellow was poor choice. The coordinate ring of the orbit closure and the coordinate ring of the orbit. Because the coordinate ring of the orbit also has a description like this. It has a different description like this, and I don't want to go into the details, but you already see that here, this description with this inner product with the superstandard tableau, you get a very similar description here for the coordinate ring of the orbit. Here it's M, and here is some projection P. P is actually even easier. It's just a symmetrization, actually. This is a slightly more complicated, like your sum over all maps. This is your sum over all permutations only. So these are extremely close to each other, these two descriptions of the coordinate rings. And this, in the second talk, this will make it possible to actually draw very close connections between these two rings. Yeah, which then leads to the multiplicity obstructions. Right? Because here, it's not, so for this one here, maybe let me say this again. For this one here, classically, because this is not a closure, the closure is usually, the closure gives us a lot of trouble. We don't really understand the closure, but if you don't have the closure, then you do have formulas for this highest weight vector space. And they are not tableau theoretic. They are completely nice formulas in terms of representation theoretic quantities like Plathism coefficients, Littlewood-Richardson coefficients, Canonical coefficients, things like that. So you do have extremely nice formulas for that. You don't have those here, but now you have a close connection between the two, because I mean, this looks almost the same as that one. And yeah, so the theorem in the second talk will reflect how very close these two rings actually are. Okay, I want to do some, in the remaining time, I'm going to give you some ideas of how one could prove a thing like this, right? This theorem here, that this is indeed the highest vector space. Just give you the ideas of the tools that are involved in having such a result. Okay, so our result, so we want to understand this highest vector space, right? This is our group orbit closure. Now, so this coordinate ring here is, yeah, you get it by projection, right? By just restricting the domain of definition, say. But this is also an image of a type of symmetrization from the tensor space of the delta times d fold tensor power of c to the m. Right? Because these are, you can think of these as tensors, but they have an additional symmetry. I mean, there's d times delta many positions. You have the small SDs that permute tensor positions, and then you have a big S delta that permutes the blocks. This is the Reith product again, right? And there's a projection, that's the symmetrization over this Reith product. And yeah, it turns out that this here, we do understand actually quite well. Actually, not only that, so we do understand this highest right vector space even quite well. So, and then what we just do is we take this highest vector space, we interpret this as functions by we interpret this as functions basically, and then we restrict the domain of definition. So there's 3 steps here. The first one is actually really nice and completely classical. It's called the sure-while duality, which is this center part here. This is sure-while duality. And it says that we know exactly how the tensor power of C to the M looks like. So this is the decomposition. It's a beautiful, and I mean, when you see this for the first time, it's extremely mysterious that this happens. So let me maybe say, so this is a direct sum, and what you would expect now is some kind of summation over some types of irreducibles of the GLN tensor, some irreducibles of the symmetric group. This is what you would expect. And there might be some multiplicities. So first of all, what you see is there are no multiplicities here. And the second thing is that whenever you have well, each lambda here is paired with a lambda. That's also completely not obvious. Why should it, right? So this is the theorem. And that, yeah, that is sure-while duality. Saying that there's no lambda tensor mu where those are not the same. And also there are no multiplicities. So this is completely understood how this looks like. And now if you go to the highest weight vector space, so if you have this theorem and you go to the highest weight vector space with respect to any mu, any nu now, this means that, yeah, so I have to take this and I have to go to the highest weight vector space of weight nu. Well, this kills off all factors or all summands here that are not lambda, and I only keep lambda. So I'm using here now that the highest weight vector space of weight nu of lambda is known. So it's actually the case that the dimension of this is dimension of, can I use that eraser? Yes. The dimension of this is 1 if in this case if lambda is equal to nu, and 0 otherwise. So this means if I take the highest vector space here and on this sum, this collapses a lot, right? I mean, all these things go to 0. 1 will survive with a vector space of dimension 1. So only actually this one last factor will survive. And so we'll only get that. It's extremely, yeah, it's extremely, there are not so many different highest weight vectors here. So I have a complete understanding of this. This implies that if I find a v lambda here in this vector space, then the only thing that I need to do to get the whole highest weight vector space, it's extremely easy to get the highest vector space. I just take this one highest weight vector. So this is an element in a representation here, and I take all its different permutations and take their span. This spans the whole representation. This is an irreducible representation. So I get it. I just permute everything, take the linear span, I get the whole space. This is now immediate from this. So perfect. So I only have to find one v lambda in this highest weight vector space, right? One highest weight vector, and I can do this. I can write one down, right? So for example, this v lambda here is in this highest weight vector space. I take a wedge product. So here I again want to have that lambda transpose is equal to mu. So I want to take the wedge product up to so along the first column, tensor this with the wedge product along the second column, and so on, and take the wedge product, tensor up the wedge products along the columns. A little computation just shows you. I mean, you just basically you literally check the axioms, and it will tell you this is the highest weight vector. Right? You just say it scales correctly, and it also if you apply the upper triangular matrices, then the wedge products will actually make sure that everything else will cancel. So if you're replacing here an E2 by an E2 plus E1, it's going to be, yeah, it's going to E1 wedge E1 is 0, so nothing's going to happen. So this is a highest weight vector. And yeah, so an example here, yeah, let me maybe, yeah, why not? This is the discriminant. So if you do E1 wedge E2, tensor E1 wedge E2, so this is, I write this out in tensor notation. And I get this, I write this also, this is like the whole long tensor here. This is the highest weight vector here. And I can now change, for example, the second and third position, and I still get the highest weight vector. It looks slightly different, right? I have changed here the second and the third position just. Yeah, here's nothing happened. It looks a bit weird, all these E1s and E2s, so it's a bit hard to see. So one has to actually use some smarter notation maybe on the next slide. So I do get these types of highest weight vectors. So I can construct them, all permutations. I just apply all the permutations that I can that are possible to this specific vector here. I get all the highest weight vectors. I mean, the linear span is literally this highest weight, the highest weight vector space. Now I want to say, okay, but how can I now go to polynomials here? Because those are tensors. So I use that I can define a polynomial by saying, if I have a tensor, V, I can define a polynomial by saying I take V and, well, the evaluation at a point Y should be the contraction of V with Y raised to the delta tensor power. That is a way of defining polynomials, and every polynomial can be defined in this fashion. And if I do that, for example, I evaluate here at x1 squared plus x2 squared, which is this tensor here. If I want to evaluate my function now that I define in this fashion, so this is like the tensor from last slide. Yeah, you might not see that this is exactly this tensor, but I want to now evaluate it at this polynomial. So I contracted with this second power here. And it's a bit, yeah, now this is a bit a smarter way of writing it, right? So 1, 1, 2, 2 becomes actually 1, 1, 2, 2 minus 2, 2, 2, 1, 1, 2, and so on. And I contracted with this tensor here. And now I can, this is just a mix, and this is just a matching thing. I'm just checking here the string matching, like 1, 1, 2, 2 is a 1, 1, 2, 2. And here I find a 2, 2, 1, 1 is a 2, 2, 1, 1. Okay, perfect. So two of them, these don't match anything over here. So I get two of those match, and this is just the scalar. So this is a half. And I can also do this on, I can evaluate on a different tensor, say on x1, x2. I can also evaluate, get the same, play the same game, get something minus 1 over 8 or something like this. And actually, this is the discriminant. So because my, yeah, so I evaluated here minus 1, 8, b squared plus a half ac is indeed just a scalar multiple of the discriminant. And there are alternative ways of calculating this. So there's a way of calculating this by keeping the determinants. So you don't have to do this whole large expansion. I mean, not in the interest of time, not go over this, but you can get the same value here by actually pushing the permutation to the other side and getting a sum of products of determinants. That's extremely helpful for computations, because of course we know that determinants are easier to evaluate than these huge tensor expansions. And we can also do it using the tableaux and the super standard tableau, right? So you will also get, yeah, you do the same type of computation, and you at the end also get a half here. So those are all possible ways of doing this, and you can define a polynomial like this. And you want to evaluate at a power sum. You want to at some point conclude that that this here, this way of doing things, is the way from the theorem, and these ways, these two ways of doing things, are the ways that are natural and come from the definition, right? You want to say that this is the same, and so how could one do this? So you're just starting with the power sum, and you just calculate. Okay, now I have to actually calculate this value, and oh, you already see that if you expand this, you get the sum over all maps. So this already looks like the thing in the theorem, right? Where you're summing over all maps, and this is exactly the sum over all maps. And yeah, so we take this vector. This is basically just, okay, I'm not saying anything smart on this slide, I think. It's literally, maybe I don't want to go over these details. So what I want to say is, if you expand this just in a very natural way, you get a sum over these maps. And there's a lemma. This is also not a smart, not a deep thing. The lemma basically just tells you that whatever you calculate here during your expansion into a tensor contraction looks exactly like a contraction of the tableau with the super standard tableau. So there's nothing else is happening here. So therefore, yeah, there's only one tiny thing that is left to be done here, which is you arrive here at some computation that almost looks correct, and then you analyze that that your sum is basically the correct sum, and that's it. So it gets a bit yeah, I'm not even sure if this is really gets really involved, because there's no deep things that are happening here. This is, you can do this completely on like basis vectors and basis tensors. There's nothing that, I don't think there's any deep theory happening here, and you'll end up with exactly the formula that you want. Yeah. So this is the last slide. So what you have here is now this vector space here, completely generated by these functions, and we've seen several examples, and you can yeah, it's completely hands-on. You can just implement these. You can do small examples on a piece of paper, no problems. You can because I mean, before, of course, it's a bit mysterious, this thing, but now this is completely hands-on, just using tableaux. And yeah, so in the second talk, we will yeah, we will see that this one here is so close to that one, and this one we do have so many other sources of information that we can actually lift this information that we have here. In particular, as information coming from the stabilizer of P, we can lift this to get actually information then here on this highest vector space. And this will enable us to actually write down completely explicitly. I mean, you can write down, this is extremely explicit, write down the exact lambdas that give us the multiplicity obstructions. And this is all completely tableau theoretic and combinatorial in the end, right? So it removes, in a sense, it removes the geometry here from the picture, right? And everything can be done here based on tableaus. Yeah, so this was a workshop talk, so it was a bit more work here. The next one will be more of a conference talk style, right? But as it is now, I thank you very much for your attention. You are muted, you're muted.
Sorry. So how do I interpret the statement of the theorem? As in, okay, so the calculations tell me, yes, I will get some functions on G. This is the way I'm going to. When you say the, yeah, so what does it mean to say the, I'm a bit confused about the, so when I mean, you're looking at number of distinct such functions.
It's the, okay, so it's, okay. So this is a vector space, and it's generated as a vector space by functions. Those functions are constant on the, or those functions are constant on the stabilizer orbit.
Okay.
Right. So this means they are each of these functions here. So you choose a tableau T.
Mm-hmm.
When you fix a tableau T, mm-hmm. then this means that you have a function.
Correct. Okay.
And each tableau T gives you a function. You take any semi-standard tableau of this properties, gives you a function. Now, you don't know if that's the zero function. That might just happen. Oftentimes, indeed, that must happen for specific reasons. But some maybe, for example, if the Plathism coefficient of that shape is just zero, then there's no way of generating any functions. But you can still write on these tableaux. This will just be end up being the zero function. So now you run over the different tableaux, you get different functions. And look at how many are linearly independent. Yeah, there might be, some might be linearly independent. So what you want to know is the dimension of the space of functions. You can get that dimension if you, well, depending on what you do. I mean, if you are on a, if you want to just know some numerical value, some lower bound, for example, if you just want to know some lower bound, you plug in some values for G, and you evaluate at different points. And you will end up seeing if your function is actually linearly, if your functions are linearly independent and what's their dimension. If you want to know the exact value, this is good for, definitely good for lower bounds. So the exact value, of course, you would have to plug in symbolic things into G. I mean, that gets us, of course, a bit more difficult.
Okay. Correct.
But
correct.
that's the meaning. So yeah, I was not so sorry. Yeah, you do for each tableau T.
Yes, I had missed
Yes,
that.
yes. Each tableau gives you I was not so clear on that. So each fixed tableau T gives you now a function. And here it's each fixed tableau S gives you a function. Those tableaus are a bit different actually from this. And this all looks slightly different, but it's close enough, right, to actually make a connection.
Yes, absolutely. Great. Lovely. Very nice talk. Thanks. So are there any more questions for Christian? A great talk, Christian.
Can we go to I think the third or fourth slide, I guess.
Yes.
I think I missed a symbol there. I thought so.
Okay, I might. Just this one here?
No.
This one?
Yeah, right, that one.
Yes.
So when we are writing V equal to direct sum of what is the subscript lambda partition over what?
Yeah, so exactly. So this could be actually any number. So what you actually get is you do get a sum over all, say, I don't know, K. And then you just put a K here.
Sure.
So and it's a partition of anything. So it's actually, so okay, let me also say this is for every polynomial, but we're only talking about those anyway. Polynomial GL representation. Then you can take actually anything, so it doesn't matter what the number actually is. So let me maybe say this here. Here's the same. Here's already this. So you have a partition that has exactly D boxes, and a partition where the number of boxes does not matter, but you have at most M rows.
Right.
There's a symbol missing here, and that is intentional. It's not that people do not write this symbol. People do sometimes are more like fancy and put the M here underneath, and that is also possible. Like that, I don't think there's a strong way for one or the other. Yeah. So this also means that for a fixed D, there's only a finite amount of irreducible representations because there's only so many partitions. But for fixed M, there's an infinite amount of irreducible GLM representations because you're not fixing the number of boxes. There's a remedy for that, because when you are so I can actually, here in this specific case, and this is the case where we can actually fix the number of boxes, because all the things that will appear, we know will have exactly delta times D many boxes. Nothing else will appear. That is just for the, already, we know this already here for this tensor space. We already know here, where is it? Here. We already know, here already. Yeah, there it is. We already know nothing more appears. So this one's already, we can only have exactly delta times D boxes. So also here, there can only be that many boxes. So also here, there can only be that exact number of boxes, nothing else. Number of boxes is precisely delta times D. And at most M rows still. So everything is, so still the number of different partitions that could be potentially be there is still a finite set from which we have to choose. Yes, well, thank you very much for that question. It was very good. Yes, I didn't always write the delta D. I should probably have done that. Yes.
Yeah, it's clear now. Thank you.
Perfect.
Yeah. Okay. Thanks, Christian. Thanks. I'll stop the recording.
Thanks a lot. Thanks a lot for having me here.